Trevor.
This video
YouTube channel. You bet. You can check them out there. Or just go to Canvas and you can check them out because I post them on there right away.
Yeah, I was like your third subscriber.
Very nice. Taylor Runge subscribed too, even though he's not even in the class. So that's pretty sweet. All right. Today,
Did we already do these?
we went through, okay, what cycle did we, or what did we talk about yesterday?
Glycolysis.
We talked about glycolysis.
Glycolysis.
Very good.
Their
Okay,
eyes.
shh, whatever. Be with me here. In glycolysis, the glucose molecule is broken into what molecule? And that's the essence of what I wanted you to get yesterday.
ATP.
Okay, some ATP could have been made, yes.
And then
Pyruvic acid. Pyruvic acid was what I wanted you to get out of glucose broken into pyruvic acid, because that's going to fuel what we talked about today. So what we're going to talk about today is essentially the Krebs cycle. One of the three biochemical pathways involved in respiration is the Krebs cycle. We have glycolysis, Krebs cycle, electron transport chain. It's pretty much opposite of photosynthesis like we talked about. All right, so we're going to go through the steps of aerobic respiration when oxygen is present. And that is what we're going to start out with today. Go through glycolysis, boom. All right, this is what we left off on yesterday. Glycolysis essentially produced 4 ATP molecules, but only had a net gain of 2. That adenosine triphosphate, or ATP, what's its purpose again in a plant cell? Or in a cell, all our cells too? Yes, energy. Energy is huge for anything, and it gives the cell energy. Pyruvic acid also is an energy source, and that is what is essentially made through glycolysis. All right. Next one we have here. This was in the cytoplasm, glycolysis happens. Now we are getting inside of the mitochondria. So the pyruvic acid has to diffuse across the mitochondria's membrane and get into the mitochondrial matrix, or just the inner part of the mitochondria. And the matrix, it says, is just simply solutions inside of the mitochondria where the enzymes, waters, and different phosphates and other things are located. But Krebs cycle takes place inside of the mitochondrial matrix. And this is just an overview. So hopefully by the end of today, all of us, if you have questions, please, and me, okay, we're going to make sense of what all this jibber jabber willy wally is. Yeah, you ever heard that one? Nope, it's a new one.
I like
So essentially what we're going to be doing is taking our pyruvic acid that we made through glycolysis. Okay? This pyruvic acid started in glycolysis, and we are essentially going to turn that pyruvic acid into NADH and FADH, and FADH isn't here, but those two are carrier molecules. We're going to carry electrons over to the electron transport chain to help make ATP, essentially. And then we're also going to be making some ATP as well, which is really right here, but this chart doesn't totally say ATP, but that's also what we're going to be making. ATP and NADH and FADH are going to then move into the electron transport chain. Okay, next slide here. First part of Krebs cycle. Boom, here it is. First step of the Krebs cycle. We have a 3-carbon molecule of pyruvic acid. That was, again, from glycolysis. All right? And that 3-carbon pyruvic acid molecule essentially loses a carbon dioxide and a hydrogen ion and just becomes a 2-carbon acetyl group, as they're saying. So just 2-carbon molecule. Then that 2-carbon molecule combines with this coenzyme A to create acetyl-CoA. So again, we're just changing molecule forms by losing carbon dioxide, losing hydrogen, gaining some carbon dioxide. Yes. Hello. Oh. Yeah. Okay, so I need to, so she can make it again, take it again. Okay. Okay, we'll do it. Yeah, well, once I do it with one, I'll do it with the other ones. So, thank you. Bye. Okay, take a quick breather. Give a neighbor a high five quick. Thank you, Keaton. I appreciate right there, right there.
Here, Trevin. You may want to put a high five up front, anybody at all. Anybody.
One more high five. There it is. Nice.
Good high five.
Okay, sorry about that. Back at it here. So, like I said, we're essentially taking molecules and we're adding carbon, getting rid of carbon to get our end result that are hoping that's going to be coming here. Okay, so we have this pyruvic acid, loses the carbon, hydrogen, and then it combines with this coenzyme A to make acetyl-CoA. This acetyl-CoA enzyme then enters the second part, which is the Krebs cycle. So we have glycolysis, this little intermediate step to make acetyl-CoA. Now we're entering into the great Krebs cycle. So we started here, we made acetyl-CoA. Now we're entering into the Krebs cycle, or the citric acid cycle, or the tricarboxylic acid cycle. We'll just, again, keep calling it the Krebs cycle. And I said all that here. Krebs, citric acid, tricarboxylic acid. I can't say that term. But that's what essentially is a Krebs cycle.
What term is it?
Tricarboxylic acid.
Tricarboxylic?
There it is. Say it again.
Tricarboxylic?
Tricarboxylic acid.
Tricarboxylic?
Yeah. Boxylic. You gotta remember that. That X is like boxylic. All right. So this is what we got. We have a 6-carbon citric acid molecule is formed when the 2-carbon acetyl group, or acetyl-CoA, combines with oxaloacetic acid. This oxaloacetic acid, 4 carbons. So 4 plus 2 equals 6. 3, that's right. 6. Okay? So now we have a 6-carbon compound called isocitric acid. This oxaloacetic acid is what's going to start the Krebs cycle, and pretty much we end with it, right? Just kind of like right there in the Calvin cycle for photosynthesis, we started with RUBP, and the Rubisco added carbon dioxide, and then we ended with RUBP. Same sort of deal here. We start with this 4-carbon compound of oxaloacetic acid, and we're going to end with it. So 4-carbon oxaloacetic acid plus 2 acetyl-CoA, or carbon dioxide, they come together, make 6-carbon compound called isocitric acid. So if you look here, we can see here, right here, 3, and loses it. So 2 plus 4, right here, 1, 2, 3, 4 carbon, 4, 5, 6. You combine those 2 to create isocitric acid. So there's 1, 2, 3, 4, 5, 6 carbon molecules in there. Everybody with me?
Yeah.
Everybody with me how this molecule is made?
Yes.
Okay. I sure hope so. Because this gets pretty intense.
No acid all?
Now, we have NAD. It accepts a hydrogen ion from the citric acid molecule, forming NADH. This NADH is going to be important for you to know what it does, because now this NADH is going to go into the electron transport chain. So this is going to take electrons and take them over to the electron transport chain.
Ooh.
All right? So there's NADH molecule right there. There's one already being made. And you can see it right here. NAD accepts hydrogen. NADH now is going to go to the electron transport chain, which is the last part of this. Oh, not yet there. Okay, next here, step 2. An oxygen molecule then moves, forming a 6-carbon, already did that, blah, blah, blah. A 5-carbon molecule of ketoglutaric acid is formed by a carbon dioxide molecule being released, and the 5-carbon compound is made. So we have CO2 being released, so thus respiration, okay? When you breathe, you release CO2. Mitochondria release carbon dioxide as well. So that is this one right here. We have 6. CO2 is released, and now we have a 5-carbon compound called ketoglutaric acid. Yes?
So this is happening all at the same time.
As the electron transport chain? Yeah, I mean, as the Calvin cycle? Yep. Because
Holy.
all the time in plants, okay, sunlight's hitting the plant, right? Excites the photosystems. It excites the electrons to move through the electron transport chain. We have NADPH and ATP being made, moving into the Calvin cycle. The Calvin cycle then brings in carbon dioxide, goes through, makes all those molecules, and we get glycerolide phosphate being made. A couple times around, we get glucose being made. That glucose molecule then gets shipped out of the chloroplast. It gets shipped in the cell. Boom! Hits glycolysis happens inside of the cytoplasm, right? We're breaking down that glucose molecule into pyruvic acid. Pyruvic acid then enters the Krebs cycle through the coacetyl-CoA, and it all is happening continuously. Because if it didn't happen continuously, this is a great question, all that energy, no energy would be made. And those plants need energy all the time. You guys have to have energy made all the time as well. Almost, even when you're sleeping, you got it. Right? Because your muscles are moving as well, and those muscles need energy at all the time.
Nope, I hibernate.
You do. Even when you're hibernating, though, you're still breathing. Unless you're the woolly bear. Now, if you're the woolly bear, I don't know. Because woolly bears can actually get frozen in ice and pretty much have no vital sign, and then they can come back to life.
Not me.
What's the target bear, huh?
Woolly bear.
The woolly bear. Should we start calling you that?
That's fine.
Bear? Okay, I'm not going to do that.
Instead of Groog and Boom.
Yeah. All right. After we have a 6-carbon molecule turns into 5, carbon dioxide released, we now have another hydrogen ion that was accepted, and we have NADH being made again. Right here. So we have another NADH molecule being made, which is going to help carry electrons to the electron transport chain. Nice. Nice job there. I mean, Keaton.
I like woolly bear.
And that's where we are. We're right here now. NADH made here, NADH made here. We got this turned in here. Okay. Now we have CO2 being released again, and now we have succinic acid that is being made into a 4-carbon compound, succinic acid. We have ATP being made here, and now we have another electron transfer carrier protein or molecule that's being made called FADH. FADH. Again, the NADH and FADH, these are simply just going to carry electrons into the electron transport chain to help power that to create ATP. So essentially, both electron transport chains make ATP. This one, though, in cell respiration, just makes a crap ton more. I'm just on record saying that, aren't I? I'll probably get
Oh,
fired.
yeah?
Sorry about that. Yeah.
Dunzo.
Last thing here, NAD accepts hydrogen ion from molecule forming NADH, and then oxaloacetic acid is made because, again, this 4-carbon compound, oxaloacetic acid was a 4-carbon compound, and that's exactly what we have made here, oxaloacetic acid. The Krebs cycle then begins and ends with this oxaloacetic acid. So essentially, we start with the 2-carbon from acetyl-CoA, combine it with 4-oxaloacetic acid. Through the different molecules that are being made, it ends up becoming back to a 4-carbon molecule, and that's oxaloacetic acid. Then we have FADH, NADHs going into the, and some ATP going into the electron transport chain. So we started with 2 carbon from acetyl-CoA right here. 2 plus 4 equals 6. And then through some NADH being made here and here, then ATP and then FADH, we get, and then 2 carbon molecules leaving. Okay, the coenzyme A is leaving. Then we come back with the oxaloacetic acid right back here to create the whole cycle all over again.
Okay, I didn't hold up.
And here it is. Here's what we have in the Krebs cycle. Okay? And glycolysis here. We have glucose molecule broken into 2 pruvic acid molecules, and then it's going to yield, and then in the Krebs cycle, 6 NADH molecules, 6 CO2, 2 ATP, 2 FADH molecules, and for a total of 4 ATP, 12 carrier proteins, 8 NADH, and then this FADH is only made in the Krebs cycle. We had 2 molecules that NADH is made in glycolysis, and all of this together is going to go then into the electron transport chain to help power this electron transport chain. Anybody know where the electron transport chain is probably going to be taking place?
Mitochondria.
It is, but what part of the
I
mitochondria?
don't know.
Think about where the electron transport chain is. The membrane. The membrane. Well, this Krebs cycle takes place in the matrix, but
I
think
knew
of,
that was a word,
that's,
so.
you're right. Glycolysis again takes place in the cytoplasm of the cell. That glucose enters into the mitochondria. Krebs cycle takes place inside of the mitochondria. Electron transport chain is going to take place on the inner membrane, just like the electron transport chain took place of the inner membrane of the thylakoid. Okay. To sum this up, I got one more video. 2 more. We got V-Money is going to explain this one more time to us. V-Money is going to be bumping again. So if you guys want to go ahead, get a little bumping going, you do it. Okay? Just be careful and not bust the move too much. V-Money. Anybody remember what are those 2 pruvic acid molecules going to be driving in today?
Energy.
They're going to be bumping in what?
The low rider.
What type of lowrider?
Mitochondria.
A pink. Oh. Jeez. Oh.
What's happening is your boy picking it back with the second video of cellular. We ended with 2 pruvic acid molecules. Well, these pruvic
Remember what they're writing in now?
acid molecules
Pink.
travel from the cytoplasm.
Ferrari.
Took place, and it travels to the mitochondria, and it travels there in a Ferrari, or at least
There it
my
is.
interpretation.
Boom.
It travels in a Ferrari. At
Pruvic acid right there. 1, 2, 3 carbon
the
molecules.
last time. The in-between step, which is in between glycolysis and the Krebs cycle, is what I like to call forming a COA. And COA just stands for coenzyme A. It's not cobalt A because there is no A, but it stands for coenzyme A. This takes place in the
Eyes up here, Hobie.
the
This'll
matrix
help
is
you out.
within a
V-Money
mitochondrial
wants you up
inner
here.
membrane. And basically, it's
Hey.
just some more cytoplasm jelly stuff. We have two pyruvic acids, one on the top, one on the bottom. These pyruvic acids will come together with 3 water molecules, which is, as you can see, I have the big O and the 2 little H's, that's H2O. And also the coenzyme A, which is a CoA, and an NAD+, which remember we talked about is just a carrier molecule. It'll come together with those, and as you can see, it produces 3 outputs. We have NADH with those 2 little circles. Remember, those 2 little circles are electrons.
Electrons
And
up
we are left
here.
with carbon dioxide as a byproduct, and also we are left with the coenzyme A with 2 carbons, because one of these carbons was used to form that CO2.
So
And
carbon dioxide's released right here as
I'm
well.
talking about either the top or the bottom. I'm not talking about both of them right now. The next slide shows the in-between steps reacting to products. This is the overall for the in-between step. This is just basically the setup for the Krebs cycle. Our reactants were 2 pyruvic acid molecules, 6 water molecules, 2 coenzyme A molecules, and 2 NAD+ carrier molecules.
To
The
get,
products were 2 acetyl CoA, which were those 2 carbon dioxides with that coenzyme A on the front, and 2 carbon dioxide molecules and 2 NADH.
boom.
This brings us to the next step, which is the Krebs cycle.
There it is.
The Krebs cycle also takes place inside a mitochondria.
Anybody ever seen that movie? The Matrix? Did you get it? Because this is going to happen inside of the mitochondria matrix. Okay.
That's pretty cool.
I thought V-Money was pretty
It takes place inside
good.
the matrix. Now, I will demonstrate one Krebs cycle. For each glucose molecule, which remember, at the beginning we started with 1 glucose molecule, the Krebs cycle happens twice, or goes around twice, once for each acetyl CoA. Now,
Or
we
pyruvic
have
acid,
2
essentially, was
acetyl
what it
CoA
was.
From our in-between step, so the Krebs cycle will go around twice for every 1 glucose molecule. So we start off with the acetyl CoA.
Anybody remember what this 4-carbon compound is, that molecule that the Krebs cycle starts with and ends with?
I'm so confused right
He said it starts with
Which one?
now. All of them.
the OC.
Yeah, oxaloacetic acid right here.
Oh, since you said that.
Think about this, Keaton. What you are doing is essentially turning molecules into other molecules to get an end result. And the end result is hopefully going to be making NADH and FADH to help carry electrons over into the electron transport chain. Because our ending result, it's kind of like photosynthesis, right? We had to go through all that stuff. We had to go through the electron transport chain, chemiosmosis, and the Calvin cycle to make what was our ending goal that we wanted to make. Which was in the form of what? Glucose, right? We wanted to make a carbohydrate. Now we're taking that carbohydrate and breaking it back down into an actual form of energy that the plant and our cells can use. Okay? But in the meantime, and what is, Keen, what is that energy source that our cells can use and plant cells can use? Can they use glucose molecule? They can't just use the molecule of glucose, no. They have to break it down into what molecule? 3 letters. ATP. Okay, so plant cells have to use ATP. Our cells have to use ATP. We can't just take glucose and just use it. It has to be broken down. And that's what this is doing here. It's taking that glucose molecule, breaking it into pyruvic acid, putting that pyruvic acid into acetyl-CoA, because pyruvic acid was 3-carbon compound. Now we're going to take this acetyl-CoA, combine it with this oxaloacetic acid to create a 6-carbon compound. All right?
Entering the Krebs cycle and coming together with a 4-carbon compound. And they make 6-carbon, except it looks a little different than the 6-carbon we saw before. It looks like the bottom right, as you can see here. And
So this 6-carbon compound that he is talking about right here we said is the isocitric acid right here. Boom. 1, 2, 3, 4, 5, 6 of them. Okay. Sorry, V-Money. I'll let you keep rolling.
And coenzyme A goes off, but it's not actually leaving. It's just being put off to the side for right now, and you'll see why later it'll come back in.
Boom, there it is.
6 carbon molecule comes together with
Coenzyme A.
plus, and it loses one of those carbons, and they form CO2 at the top, and the NAD plus turns into NADH with those 2 electrons. Then we are left with a 5-carbon molecule. Then that 5-carbon molecule comes together with NAD plus and a COA, and what we get formed from that is we get carbon dioxide, 1 carbon dioxide molecule, we get 1 NADH molecule with those 2 electrons again,
Boom,
and
boom.
we get the COA or coenzyme A with a 4-carbon
Oh, wait, right here.
tail
My bad.
in front of it. The coenzyme A and the 4 carbon molecules then meet up with an ADP tail.
I'll go back to this here. So this one, right here, this 6-carbon compound, this isocitric acid, is then a carbon dioxide is released. So carbon dioxide is released here. We are then left with a 5-carbon compound, which is this ketoglutaric acid right here. Okay, just again, another molecule leaving, we're moving carbon out, and we're just making a new molecule to get our end goal, essentially, of this one of getting NADH and FADH, okay? Just steps along the chain to hopefully, at the end, get our ATP that's going to be made. Then we have NADH being made here, and then also right here. Boom, and then it's going to go into
And we get
the
COA or
FADH being
with
made.
a 4-carbon tail in front of it. The
Right here.
coenzyme A and
ATP
the
is
4
being
carbon
made,
molecules then
and then
meet up with an
FADH.
ADP and a phosphate group and form ATP while it loses the coenzyme A. So we are left with a 4-carbon molecule. That 4-carbon molecule then moves on and comes together with an NAD plus and an FAD. Now, whoop, whoop. This is the first time we've ever seen the FAD.
V-Money into it now.
Don't get scared. It's just another carrier molecule like NAD plus.
There it is, just carrying.
So that 4-carbon molecule comes together with those 2, and it produces NADH with the 2 electrons, a 4-carbon molecule, and an FADH2 with also.
Anybody ever flown before?
Yeah.
Okay. Has anybody ever lost their bags?
Yes.
Yes.
Are you serious?
Yes.
Okay, tell me your story.
I was pretty young, but I remember that we were like running around my family and I was like chickens with our heads cut off trying to find these bags, and they ended up on a different flight.
Oh, dear
They
Lord.
somehow did end up in the same airport, but they were in the wrong area because it was a different flight. It was nuts.
Tell me your story.
When I went to Mexico and it was my brothers.
You lose them going there or coming? So going there.
No, we lost him coming back, I'm pretty sure. Because my brother was being dumb and he left
My brother's never
the
dumb.
carry-on on the thing. And so they took him off, after we had gotten off. And then we got like all the way through the airport and Josh realized that he didn't have his stuff. And
So that wasn't really the,
up to Omaha.
that wasn't the airplane's fault totally
No,
then,
it was
huh?
my brother's fault,
Okay.
But they did take it and they put it in another area. Like they.
But it wasn't on the luggage deal, huh? Luggage claim deal?
Mine weren't really lost. Some weird days took mine.
You what?
Like he took my bag.
Off the luggage rack? So that, again, wasn't the airport's fault then, huh?
Some corny dude that felt like he had something to do.
Okay.
Delaney has a story too.
You got one. You lost baggage?
Get it. Get it.
On our way to Florida, he didn't have his bags, whatever. Like they were on a different plane. But he obviously put his stuff in one pile and he went on a different plane.
Oh, no. So that was his fault there. Okay. So those stories, the reason why I asked is because I wanted to connect it with this, even though only really like one of them I think would be like this. But what? How can you connect losing luggage to this Krebs cycle here? Okay, so I essentially was going this way. We'll go with Ashley's story since hers was really the only one that was kind of like the airport's fault. If that airport baggage claim, you could think of those as the electron carrier molecules, all right? Because those electron carrier molecules are essentially just going to carry those electrons over to the electron transport chain, such as when you put your faith in the airport to actually take that, or the airline, and put your bag in that little check-in part, and they're going to put it on the airline. If they don't do that right, then it ends up in some, what did you say? Corny dude's hands, okay? But if they do it right, like in the Krebs cycle here, these electron carriers are taking those electrons, taking them into the electron
Two
transport chain.
electrons there. This slide is the overview.
Last deal here. This is what we
The
get from the
reactants
Krebs
are
cycle.
2 acetyl-CoA, 6 NAD+, 2 FAD, 2 phosphates, and 2 ADP. And the products are 2 coenzyme A molecules, 6 NADH molecules, 4 carbon dioxide molecules, 2 FADH molecules, and 2 ATP. Now the net is
ATPs.
also 2 because we did not enter any ATP.
Just after this is done, then
into
you
the
can
Krebs
go.
cycle.
Unless it's in like emergency.
We did in glycolysis.
Or-
This brings us to our last step, which you will see in the next video. So don't go anywhere.
Last step.
Click on the next video.
Last step is the electron transport chain. All right, what do we got here? 2, 4, 6. What? Yeah, we can go to the front part here again. Even though this one's not as good as yesterday's. We can bump, yeah, this one here real quick. There it is. There it is. Yep. Okay. All right, any questions on this here? Any questions? Right here. Boom. All right, here's what I want you to do. I want you to partner up with somebody. Partner up with somebody. Anybody.